Hello, we've got a revision lesson now for reversible reactions, so Year 11 Triple Science Chemistry. And in this video, we're going to revise 4 things. We're going to look at the effect of changing pressure on a reversible reaction, little typo there, the effects of changing temperature, the production of ammonia via the Harbour process, and the production of sulfuric acid via the contact process. All of these 4 things you're going to need to know for your upcoming test. So I'm going to talk you through them. I'm going to give an example for both things on the pressure. I'm going to give you the laws. You're going to need to know those laws for your core knowledge test. I'm going to talk you through the steps of both processes. And then finally at the end, we're going to look at some past paper questions. So the first thing we're going to look at is reversible reactions and pressure. Okay, and the first thing I want you to be thinking about in terms of pressure, before I even look at those rules, is that keyword pressure there means we're going to start counting what is on, in terms of the number of moles, what is on either side. Okay, so I can see on this side I've got no number, which is 1 plus 1, so I've got 2 moles on that side. And on the right-hand side, I've got 1 plus 3, so I've got 4. Okay, and that's really useful because all my rules are about the number of moles. If I increase the pressure, I move to the side with the least moles, okay? And when I decrease the pressure, I move to the side with the most. Now, if the numbers on either side were the same, nothing changes. Pressure has no effect at all on yield. So first thing, I've got predict the effect of increasing pressure on the yield of hydrogen gas. So first of all, I know I'm going to move to the side with the least moles. And out of my equation, CH4, H2O, CO and H2, hydrogen gas is H2. So first thing I wanted to spot then is that the least moles is on the left. Okay, so first thing I'm going to do is my equilibrium shifts to the left-hand side where there are fewer moles. And as a result of that, if we now look for H2, we can see H2 is actually on the right-hand side, isn't it? So what that means is H2 is on the right and my equilibrium is moving to the left. That means anything on the right, my yield, how much I'm producing is going to go down, whilst everything on the left where I'm moving to goes up. Okay, so if I'm moving to the opposite side, the amount of what I've got left decreases. So my last bit then is this means, because H2 is on the right-hand side, the yield of H2 decreases. Now that is an example there. To show you how to do that, the laws are the most important thing to remember, and they're going to be really useful. So make sure you've got all of this written down in your notes now. After doing pressure, I said we were going to move on and look at temperature. Okay, so my rules to remember this time, really important once more that we know them. If I increase temperature, I move to the endothermic side. And if I decrease temperature, I move to the exothermic side. So really important you know that, and you've got that law in your head. I've got the same reaction here, but I've got predict the effect of decreasing temperature on the yield of hydrogen gas when the production of hydrogen is endothermic. So first thing I'm going to look for is I can see hydrogen is on the left, okay? And the production of hydrogen is endothermic, so that means that this side is endo and my opposite side is exo. I can see I am decreasing the temperature. And that means when I decrease the temperature, I move to the exothermic side. Okay, so I'm going to move exothermic. And I can see my exothermic side is on the left. Okay, so my answer to this one, predict the effect of decreasing temperature on the yield of hydrogen gas when the production of hydrogen is endothermic. I'm going to shift to the left-hand side as it is endothermic. And again, we saw previously in that first example, hydrogen is on the right, which means if I'm moving to the left-hand side, hydrogen will decrease. So as you are moving to the left-hand side, hydrogen, remember that is on the right-hand side, yield decreases. So again, you really, really need to know these laws. So, so important. Now, we're going to move on we're going to talk through the Harbour process. I mean, you need to know step by step. In your test, there is a question step by step on the Harbour process. So first thing we need to know, really, really important thing, is I use the Harbour process to make ammonia from nitrogen and hydrogen in the general equation. This is my general equation. It's a reversible reaction, okay? I've got only things which are gases. And my first thing which I need to do in my Harbour process, and I've got a little diagram showing it on the right as well, is that hydrogen from natural gas and nitrogen from the air are pumped into the compressor. And as we move into step 2 into the compressor, I'm going to compress it to 200 atmospheres pressure. So I'm going to have a really, really high pressure. After pressurizing them, I'm then going to move them into this tank here. And there's some iron catalyst beads. Remember, catalysts are going to speed up the reaction. And this is going to take place at 450 degrees Celsius. Okay, so this is really, really hot. And I'm doing that to increase the rate as well. So I've got a catalyst, and I'm also hot, and that's to have a speed up. Okay, I want to speed up those rates. Now in step 4, as it's in this thing, in 3, I'm making ammonia. So this reaction takes place in 3, okay? But obviously, not all of that is going to react. It's never going to be perfect. So what's actually going to happen is I'm going to have a mixture of ammonia, hydrogen and nitrogen. So in step number 4, I cool it. And what happens is that my ammonia turns into a liquid, which is shown down by here where my lightsaber is. And I filter that off. And then 5, any of my nitrogen and hydrogen which are left, I then recycle back up to the top. Okay? And we keep repeating this to make sure as much as possible is there. So you need to know the equation. You need to be able to tell me these 5 steps. You need to be able to tell me that it's at 450 and has a catalyst to increase the rate. Okay? I've then got the contact process. So again, you need to know these 3 steps and the equations. So the first thing we need to know is these 3 things. These are my raw materials. So we make sulfuric acid from sulfur, air and water. And in step 1, the first thing I do is burn the sulfur and air to make sulfur dioxide. Okay? And that sulfur dioxide leads to acid rain. Okay? Because it leads to acid rain then, I'm going to make sure that I keep it airtight. Okay? I'm then in a reversible reaction. So step 2, I had a problem with my symbols. So can you make sure that when you write your equation, you've got a reversible reaction symbol? I react sulfur dioxide with more oxygen, and that's to make sulfur trioxide. Okay, so I've got SO2, should be a little 2, di, 2, tri, 3 oxides. Okay, so I react that to make sulfur trioxide, which is here. And I need these following conditions, and you need to know this too. I use a vanadium oxide catalyst and a high temperature. That is to speed up rates. And I use a pressure of 2 atmospheres, okay? Now, if we were doing our counting method, we know that from what I just told you, when I increase pressure, I move to the side with the fewest moles. Well, I know I've got fewest moles on the trioxide, but a problem is that trioxide is very explosive. So I use a low pressure. And my final step, I react sulfur trioxide with water. okay? And this produces sulfuric acid. What we need to know is this is an exothermic reaction, so it's very, very hot. And my sulfuric acid, rather than being in a liquid like we see it in the classroom, it comes out as clouds of steam in a poisonous cloud, okay? So again, I need to make sure until it's cooled, I keep it airtight. You need to know all of this for your test. Everything on that page you need to be able to remember, okay? Equations, we need to know, okay? We also need to know what's happening, and you need to know these 3 bullet points for the conditions for the reversible reaction. Okay, we're going to move on to some past paper questions. I've pre-done them, so I'm going to talk you through my answers each time. So this is, again, the contact process. Concentrated sulfuric acid is manufactured industrially by the contact process. It occurs in 4 stages, and it requires 3 specific conditions. We, in our exam board, only need to know 3. Okay, so I've changed it to 3. Describe the chemistry, and your answer should include the following: balanced equations, names of reactants and products, identification of the stage, and details of the conditions. So I've got stage number 1. I'm going to burn sulfur in air to produce sulfur dioxide. And look, I've got a balanced equation. So sulfur plus O2 gives SO2. My second stage in the contact process is I react sulfur dioxide with oxygen to produce sulfur trioxide. And look, I've made sure, again, it's balanced, and I'm going to actually check. I've made a little mistake in my one here, so I'm just going to make sure I've got that in right. Make sure we got 2s there. And because it's a reversible reaction, I've then spoken about the 3 conditions. I know I've got vanadium oxide, I use a high temperature, and I have a low pressure to compromise yield but prevent explosion. So that's my conditions for that reversible reaction. My final stage is I'm going to react sulfur trioxide with water. And that's going to produce sulfuric acid. Okay, so that's your model answer for that one. And just to go through, the best way to complete this booklet now is actually to be having a go at the question and then pausing the video and then look at the answer after you've had a go. Okay, using those notes you have just made. We can move on to the next one. In a closed system, a reversible reaction will form an equilibrium mixture. Write the following statements that are true for equilibrium. Okay, well, I want you to think equilibrium, equal, same. Okay, so it can't be number 1 because it's faster, so that's not the same. Number 2, it will not change if more product is added. Well, it will change because I'm changing a concentration. The concentration of reactants does not change. They're reacting. My 2 which are correct are the 2 with the same statement. My rate of forward and backward are the same, and my concentration are the same. Okay? Now, I've got this one. I've got my workings all up ready for you, but so we can talk through. So methane is a fuel made by the reaction between carbon dioxide and hydrogen. Paul predicts that the reaction is exothermic and that there are more moles on the right-hand side of the equation. Okay, so he predicts that. Okay, so what we're going to talk about now is whether Paul is correct, and we've got some graphs for this. So our task here then is to look at these graphs and work out, is Paul correct or not? So I've got a graph on the left, which is pressure, a graph on the right, which is temperature. Okay, so the first thing he said, he reckons there's more moles on the right-hand side. Okay, well, we can see that my percentage of methane is going up in this graph, okay? Which means that it's shifting to the right-hand side, okay? Because methane in my equation is on the right. And my key thing for us to spot here is that if I increase pressure, I should increase the yield, but different to Paul's thing, because when I increase pressure, I move to the side with the fewer moles. Paul reckons there's more moles on the right-hand side, while the graph is suggesting the opposite. Okay, so that means Paul is incorrect. And secondly, we're going to talk about the temperature, and he thinks that the reaction is exothermic. So an increase in temperature would decrease yield if my reaction is exothermic. And I can see that because if I increase temperature, that means I'm going down And if I increase temperature, my rule, remember, is I go to the endo. So if I'm going down, that must mean my reaction, which has methane on, is exothermic. Okay? So Paul is correct on that front. He's incorrect on the pressure, but correct on the temperature. Question number 2, I'm going to skip to the questions for you and then show you. So the percentage yield and position of equilibrium change with temperature, pressure and concentration of carbon dioxide, described by the yield of methanol changes with temperature and with pressure. Describe, so we got one thing to do there. Describe how and explain why the position of equilibrium changes is an extra carbon dioxide. So I'm going to look at that table. I've got to look at temperature and pressure. When I looked at that table, I spotted as I increase pressure, my percentages are going up in every column. And as I increase temperature, my percentages are going down. So that's the first thing I've spotted. So in my answer, I've put from the table, you can see as pressure increases, the yield of methanol increases. And from the temperature, you can see as temperature increases, the yield of methanol decreases. Okay? My next thing is I need to describe how and explain why the position of equilibrium changes as extra carbon dioxide is added. Okay? And my key thing is here, if I add more of something, okay, so I'm adding carbon dioxide, which is on the left. If I'm adding more of that, that means I'm going to move to the right, okay, so I'm increasing the concentration of the thing on the left, so that means I'm going to end up making more of the thing on the right. So your answer should say if carbon dioxide is added, the concentration of CO2 will increase. This will shift the equilibrium to the right hand side. Part B, Phil works as part of a team of research chemists. It is a good idea for scientists to work as part of a team when solving problems. Explain why. This is all about reproducibility, so we need to be comparing results. Okay, that's why it's good to be working as a group. If you ever see something about a group or maybe several scientists working together, that's what you're looking at writing. Okay, now if I skip to the questions, remember I don't like reading all the blurb until we need to use it. A, which of the following conditions gives the highest percentage in ethanol? So I found it, I circled the highest one, which is 60. And I spotted with 60, I have got a low temperature and a high pressure. So B, okay, high pressure, low temperature. The conditions used for making ethanol are 300 degrees Celsius and 60 atmospheres pressure. Suggest why these conditions are used even though the percentage of ethanol is only 20%. Okay, and my two reasons are I have a higher temperature to increase the rate, and I have a lower pressure than, because look, we did get to 80. I have a lower pressure though because I want to reduce the cost. It costs a lot of money to pressurize things. So those are my compromises. 3. So I've got a equilibrium reaction and a few tables. We're going to need to know all of that. So I'm going to go to the question first. Describe and explain the pressure and change in the temperature affect the position of the equilibrium in the reaction between nitrogen and hydrogen. So I've started off with pressure and I'm looking at table 1. Okay. So the first thing I spotted was that as pressure increases, the yield increases also. So I've written that down. As pressure increases, the yield of ammonia increases. And then I've got to explain it. So I've gone up to my question and my equation. I've counted because it's pressure. I've got 4 on the left and I got 2 on the right. Remember, when I increase pressure, I shift from the left to the right. So that means the reason, because there are fewer moles on the right hand side. Okay, so there's your answer for part 1. I've then done the same for temperature. So I go over to table 2, which is temperature. And I can see as temperature is increasing, the percentage yield of ammonia being produced is decreasing. Okay, so that's the first thing I've written for some marks. As temperature increases, the yield of ammonia decreases. And now I'm thinking of my rule. If I increase temperature, remember, if I increase temperature, think of those notes we just made. I shift to the endothermic side. Well, I can see from this reaction, it is exo for the forward reaction, which means it must be endo. So that means if I'm increasing temperature and I'm going to shift to the endothermic side, I'm actually shifting to the left, away from ammonia. Okay, so your final bit of that answer is as temperature increases, the yield of ammonia decreases. This is because the production of ammonia is exothermic, and when temperatures increase, it shifts to the endothermic side. And just to make that really clear, that is the right-hand side, RHS. We've got another one of these table questions now. So again, ignore the bit at the top until you have to. A, what happens to the percentage yield as the pressure increases? So pressure's increasing down, my numbers are also all going up. So my percentage yield is increasing or increases. And what happens to the percentage yield as the temperature increases? So left to right, I can see as temperature's increasing, my numbers are all getting smaller. So it decreases. Okay? B, the highest percentage yield is achieved with a temperature of 200 degrees and 160 atmospheres. The actual conditions are to make ethanol a catalyst, a pressure of 70 atmospheres and temperature. Okay, use ideas like percentage yield and rate to explain why each condition is used. Okay, so first of all, I use a catalyst to increase rate, so I've spoken about that one. I have a pressure, a fairly high pressure to increase the yield, and to prove that, I know that I've got fewer moles on the right-hand side. Remember, increase pressure, shift to the side with the fewest moles. And look, I've got 2 and 1. Okay, so I'm always going to go to the right if I increase pressure. And I use a high temperature to increase the rate. Okay. C, the process is automated. Explain why automation is used. No human error. Okay, we're taking out any sort of mistakes that could be made. Next one. Sulfur trioxide is produced by reacting sulfur dioxide with water. The reaction takes place in industry at 1 to 2 atmospheres pressure and can reach a dynamic equilibrium. Explain the effect of the attainment of equilibrium if the process is carried out. Okay, so how quickly are we going to get to the backwards and forwards being equal? Okay, well, first of all, I know the equilibrium, if I increase pressure, I will shift to the side with the fewest moles. So I've done my workings, 3 and 2, so I'm going to shift to the right, as there are fewer moles. As a result, my production of SO3 increases, and that also means that my speed at which equilibrium is formed will increase, because I'm going to make a lot of trioxide, so I'm going to be able to have a backwards and forwards reaction going quickly. What volume of oxygen in centimetres cubed would react completely with 500 centimetres of sulfur dioxide? Well, what I did, and my workings are here for it for you to see, but in my equation, for every 2 dioxides, I've got 1 oxygen. Okay, so that's going to mean I'm going to need twice as much sulfur dioxide as oxygen. So if I've got 500 centimetres cubed of dioxide, that's actually going to mean I'm going to need 250 centimetres. And 250 centimetres is half of 500. And when there are alternative methods of producing a product, the final pathway is chosen by considering atom economy, cost, yield, and rates. State another factor that should be considered, safety, because we know sulfur trioxide is explosive. Okay, so that's my one other consideration. And our last question, I believe, our last one. The reaction between nitrogen and hydrogen is exothermic. If nitrogen and hydrogen were reacted at 150 atmospheres pressure and 300 without a catalyst, some ammonia would be formed. In the Harbour process, a presence of 150 and temperature of 450 degrees Celsius are used in the presence of a catalyst. Explain why the conditions used in the Harbour process are better than the first set. So first thing is we know that 150 atmospheres pressure are good because it increases yield. And look, remember, you increase pressure, you shift to the side with the fewest moles. I've got 4 on the left and 2 on the right. So that's what I've done there. But the big difference between these is that I use a higher temperature in the Harbour process. Well, first of all, we need to know that both 300 and 450 will decrease yield because I will shift to the endothermic side. And I know that because they told me it's exothermic. So if I increase the temperature, I'm going to go to the left. But what's really important to know is that we prefer 450 because it increases the rate of reaction. Okay, so that's the big thing we're looking for there, is increasing the rate of my reaction. Hope this has been helpful. You're probably going to have a test next lesson, okay? So if you need to take things home and learn them, the questions are going to be very similar to the ones which you've just done in your booklet, okay? They will also touch on the things which I said that you have to know when we were doing our notes, okay? So take this away now. Please make sure it's useful. If you've got any questions, go and see one of your science teachers. Okay, thank you. Bye-bye.